Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a post video for all the stuff you've done in calculus up to this point, which would include graphing using calculus, because some of those techniques are going to be necessary for you to do optimization problems. Now, optimization problems really sound terrible, and if you open up a textbook, honestly, it looks like a ton of word problems, and they are word problems. But there is a suggested tactic for setting up and solving optimization problems. Specifically, I have just written out the tactic that I kind of teach my students here, and this is very much in line with how I attack related rates problems. I like the symmetry of it, and so we'll talk about this here. One thing you need to know about optimization problems, the ultimate goal is to find out when a variable, let's say area or volume or cost or profit or whatever it may be, distance, let's just say, is maximized or minimized. And if you think about that in terms of everything you've been learning in calculus so far, that means you're looking for an absolute maximum or an absolute minimum on a given interval. Technically, you really don't quite need all of the material from the graphing using calculus topics, because honestly, all you really need are absolute maximums and absolute minimums. Which basically means that you just need the extreme value theorem. On a closed interval, a continuous function that's differentiable will achieve its extremes. And even then, you don't need it to actually be differentiable. You just need a continuous function on a closed interval. So it could have some type of corner or kink or cusp there or something like that. All you need is continuity on a closed interval, and you will have a maximum, absolute maximum that is, or an absolute minimum on that interval. Remember, you always check the edge points as well. So let's see, how do you attack the optimization problems? First thing you should always do, and this is kind of the required win, is that you're going to read the problem. If you don't do that, you're just not doing the problem. Second thing you need to do is understand what the problem is asking or what it's stating. That might require you to reword the problem. You're definitely going to have to draw pictures for most of these problems. You can look up definitions, for example. Maybe something is confusing to you. You might want to look up a definition to see what they mean by, I don't know, marginal cost or something like that. So all of that stuff is kind of necessary to pull things together. Step 3. Again, I kind of copied this from my related rates how-to. So some of this is more applicable to related rates, but it still applies to optimization problems. Label any unknowns and list the given information using variables. In this case specifically, you're going to state what needs to be optimized. So if they say maximize the area, you definitely want to just say, well, area, right? And if it's a rectangular area, it's length times width. Or if it's a circle, it's pi r squared, or whatever it may be. You need to develop a formula for what is being optimized. And let's see, write a master equation. That's kind of what really I'm stating right there. So write a master equation for the variable to be optimized. So again, if you're optimizing area, write down an area formula, volume, whatever it may be. And then step 5, normally after the master equation with related rates, I have a rate equation in this step, but here we're not doing related rates. Instead, we're doing optimization. So the equation in step 4, your master equation there for the variable that needs to be optimized, likely has too many variables. So for example, the volume of a cylinder. The volume of a cylinder is pi r squared h. We have 3 variables in this equation. We have a v for volume, r for radius, and h for height. And you do not want to do an optimization problem, or pretty much a calculus problem at this point, that is, with an equation involving more than two variables. So you want to reduce that down to an equation only with two variables. And there usually is some extra information handed to you so that you can relate out one of those variables. That's called the relating equation. They might say the height is always 4 times the radius or something like that. So then in that case, I would replace h with 4 times the radius, and now I can optimize this equation, or whatever it may be. Finally, after you've built your equation, really, you just find the optimal solution by using calculus to determine the absolute extrema. Now, that is actually often not a difficult step, and sometimes you're just using logic here. So remember earlier in our video series, when we were finding absolute extrema, we were testing both the endpoints of this closed interval for this continuous function we were handed, and then finding the critical numbers and testing the function at those critical numbers. And whatever the greatest value was, that was the absolute maximum, and whatever the minimum or the smallest value was, that was the absolute minimum. Well, in a lot of the application problems, your curves will only have one critical number. And if you're trying to minimize, that critical number is likely going to be the absolute minimum. Now, I'm not saying it's always the case, but for the most part, whatever critical number you get is the optimal solution. So that's just a heads up. And finally, you want to state your solution. Okay. One thing I want to mention before leaving this video, and this video is just to talk about this how-to, so we're pretty much done with it. One thing I want to mention before I walk away from it, that step 3 doesn't get used very much with optimization problems. It does get used, but not a lot. So don't place a lot of emphasis on that third step. Really, just create an optimization or master equation and then relate out any extra variables that are there. All of this will seem vague, just like when I said this for related rates, until we start using it. And then once we start using it, you'll see it actually does kind of roll out very nicely. I broke up the videos in this series into what is being optimized: area, distance, volume, business applications, whatever it may be. All right, so I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.